Hi, and welcome to the Dividing Polynomials lesson. My name is Josh, and I'll be your instructor today. First, we have to ask what polynomials are. Polynomials are basically just things with x's and or exponents on those x's. For example, x is a polynomial. We also have negative 3x is a polynomial. X squared is a polynomial. 1/2 x plus 3 is a polynomial. You can have a plus in there. X squared minus x plus 3 is a polynomial, and even something crazy like negative 3x to the 5th minus 4x plus 57.5 is a polynomial. Note there can also be constants in those polynomials, which is where the 3 and the 57.5 come from. Now, what can we do with polynomials? Well, we can add and subtract polynomials. For example, we have 2x, a polynomial, plus 3x, another polynomial, is equal to 5x. We can also do negative 4x squared plus x squared minus 2. The x squared terms combine to negative 3x squared, and the minus 2 stays the same, giving us negative 3x squared minus 2. We can do 5x plus 1 minus 4x minus 3, and then when you combine like terms, you get x plus 4. We can also multiply polynomials. For example, we can do x times 3x, which is equal to 3x squared. We can do x squared times parentheses 5 minus 3x, which is equal to 5x squared minus 3x cubed. You just distribute the x squared. You can also do more complicated multiplication. 2x plus 1 times x minus 3, you'll have to use FOIL. First is 2x times x. Outside is 2x times negative 3. Inside is 1 times x. And last is 1 times negative 3. When you do the multiplication, you get 2x squared minus 6x plus x minus 3. And then when you combine like terms, you get 2x squared minus 5x minus 3. That's not all you can do with polynomials. You can even treat them like functions. For example, we can write a function p of x and set it equal to the polynomial x squared plus x minus 1. And then we could plug in 2 for x in order to, find the output. P of 2 is equal to 2 squared plus 2 minus 1. We just plugged in 2's for x's. When we simplify, that gives us 4 plus 2 minus 1, which gives us 5. So we've done a lot of things with polynomials already. Now, let's try making fractions out of them. Specifically, they're going to be called algebraic fractions, and they're just going to be fractions made out of polynomials, a polynomial on the top and on the bottom. For example, x over x plus 1. X is a polynomial, and x plus 1 is a polynomial. You can also have x plus 2 times x plus 3 over x squared. When you multiply at the top, you'll get a polynomial, and x squared is already a polynomial. You can have x squared minus x plus 3 divided by 2x squared plus 3. Both the top and the bottom are polynomials. And you can have x squared plus 5 over x minus 1. Now, algebraic fractions are fractions, and you might be wondering, well, do the things that I know about regular fractions still apply to algebraic fractions? And yeah, they do. Just like regular fractions, you can simplify them. For example, with regular fractions, we might have 4/6. And in order to simplify them, we would factor out a 2 from both the top and the bottom, and then cancel out the 2, leaving us with 2/3. Again, we found a common factor and we canceled. We can also expand algebraic fractions. For example, we have our 2/3, and we can multiply the top and the bottom both by 2, which gives 4/6, the thing that we found. We could have also multiplied both the top and the bottom by 3, which gives us 6 over 9. We could have even multiplied the top and the bottom by 4, which would have given us 8/12. And we could go on like that, just multiplying the top and the bottom by the same thing. We can do all of these things with algebraic fractions as well, and you'll see how to do them. We'll start with simplifying algebraic fractions. In order to do that, it relies on finding common factors and canceling. Sound familiar? It should. That's exactly what we did for regular fractions. Let's try a practice problem. X squared plus 5x plus 4 over x squared plus 3x plus 2. We're given that expression, and the question asks, which of the following is equivalent to the expression above? And then we get a bunch of answers with x's in them. So what's the plan in order to solve this problem? Well, first, we're going to factor the numerator and denominator, and then we're going to cancel any common factors. This is the same as we did for regular fractions. Now, if you need a review on factoring, review the Solving Quadratic Equations lesson. There is a small lesson on factoring in there. Okay, step 1. Factor the numerator and denominator. Well, the numerator is x squared plus 5x plus 4, and the denominator is x squared plus 3x plus 2. So we're going to factor these one at a time. If we factor the first one, we get x plus 4 times x plus 1. And if we factor the second one, we get x plus 2 times x plus 1. And we can plug these into our expression for the numerator and the denominator. So our original expression gives us x plus 4 times x plus 1 over x plus 2 times x plus 1. And now we can cancel any common factors. Both the top and the bottom of our expression have an x plus 1 in them. So we can simply cancel them out. And then when we do, we get x plus 4 over x plus 2. And if we look at the answers, that's answer C. So C is the correct answer. That's all it takes to simplify algebraic fractions. Factor out the top and the bottom as much as you can, and then cancel any common factors. Okay, now that we've tried simplifying, let's do some adding and subtracting algebraic fractions. And this is where expanding algebraic fractions will come in handy. Here's the problem. We have the expression x plus 5 over x squared plus x minus 2 minus 1 over x squared plus 3x plus 2. We're asked which of the following is equivalent to the expression above. That's just asking us to simplify all that by adding. And then we get a bunch of answers. Here's the plan. First, we're going to factor the numerator and the denominator of each fraction and cancel any common factors if we can. These are exactly the same steps that we took when we were doing simplifying algebraic fractions, and that's because the first step to adding and subtracting algebraic fractions is simplifying. Next, we want to circle any factors in each denominator that isn't in the other denominator, and that's a little confusing, so we'll point that out especially when we do this problem. Next, we're going to multiply the top and bottom of each fraction by any circled factor in the other fraction. And this will give the fractions common denominators, just like we need whenever we add or subtract regular fractions. Next, we're going to subtract the fractions across the numerator, expand the numerator, and then, if necessary, we can refactor and cancel out any factors and then expand, just all stuff at the end that we might have to do to get our answer to look like their answers. First, we gotta factor the numerator and denominator of each fraction. Well, our first fraction is x plus 5 over x squared plus x minus 2. And we can't factor the numerator, but if we factor the denominator, we get x plus 2 times x minus 1. The second fraction is 1 over x squared plus 3x plus 2. And we can't factor 1, but if we factor the denominator, we get x plus 2 times x plus 1. So we can take our original expression and plug in what we just found, and that becomes x plus 5 over x plus 2 times x minus 1 minus 1 over x plus 2 times x plus 1. Note, even though there are no x's in them, constants like 1, like on the second fraction, are technically polynomials. Just don't worry about that. Now we're going to cancel out any common factors that we can find in each of the fractions. So here's what we had. The numerator and the denominator of the first fraction have no common factors. The same with the second fraction. So actually we can just skip this step entirely, and it's always nice if we don't have to do work. Now we're going to do the hard thing. We're going to circle any factors in each denominator that isn't in the other denominator. So here's what we had. We're going to start with the first fraction, x plus 5 over x plus 2, x minus 1. The denominator of that fraction has an x minus 1, but the second fraction doesn't have an x minus 1. So we should circle that x minus 1, and we'll draw it down here. Next, we'll look at the second fraction. that fraction's denominator has an x plus 1, which the other denominator doesn't have. It only has an x plus 2 and an x minus 1. So we should circle that too, and we'll draw it right here. And now the really hard part. Multiply the top and bottom of each fraction by any circled factor in the other fraction. Again, here's what we had. We should multiply the first fraction by x plus 1 over x plus 1, since x plus 1 is circled in the other fraction. And this is what we get. We get x plus 5 times x plus 1 over a bunch of stuff. And then second, we should multiply the second fraction by x minus 1 over x minus 1, since x minus 1 is circled in the first fraction. And when we multiply that out, we get x minus 1 over a bunch of stuff. But notably, it's the same bunch of stuff that's in the denominator of the first fraction now, which means they now have a common denominator. Therefore, we can write x plus 5 over x plus 2 times x minus 1 minus 1 over x plus 2 times x plus 1. We can write that as x plus 5 times x plus 1 over x plus 2, x minus 1, x plus 1, minus x minus 1, x plus 2, x minus 1, x plus 1. And now these fractions have the same denominator, like we just said. And so we can finally subtract our fractions. Here's what we had, and since they have the same denominator, we can subtract, giving us x plus 5 times x plus 1 minus x minus 1 over that denominator. And yeah, we finally were able to subtract, and now we just got to simplify. Usually we have to expand the numerator, so we have this. We should multiply the x plus 5 times the x plus 1, which will give us x squared plus 6x plus 5, and then we could subtract the x minus 1, which gives us x squared plus 6x plus 5 minus x plus 1. Remember, the minus signs cancel out and become a plus, which gives us x squared plus 5x plus 6 over that big denominator. This doesn't look like any of our answers just yet, so we're going to move on to step 7, which is refactoring the numerator and canceling out any factors that we can, and then expanding. So here's what we had. We can factor the top, actually, into x plus 2 times x plus 3 over x plus 2 times x minus 1 times x plus 1. And both the top and the bottom have a factor of x plus 2. So we can cancel those out, which gives us x plus 3 over x minus 1, x plus 1. Now, this still doesn't look like any of the answers, so we're going to do the last thing that we can do, which is to try expanding out the denominator. So we had this. We should multiply the x minus 1, the x plus 1, which gives us this. And when we combine like terms, we get x plus 3 over x squared minus 1. And that actually is answer choice D. So that's the answer. It is a long process, so memorize it if you can. Practice a bunch of practice problems. We have a lot of them in the text lesson and in the quizzes. Now, we've been talking a lot about fractions, and fractions are basically division, right? It's one thing divided by another. But what if we don't want to keep the algebraic fractions as fractions, but, actually want to divide them? Then we need to use polynomial long division, which is really scary at first, but better once you've gotten used to it. First, let's review how long division works with regular numbers. Let's find the value of 325 over 3, which is 325 divided by 3. So we write it like this. We have this sort of L with a 325 under it and a 3 to the left. Just a couple of vocabulary words. The thing being divided is the dividend, and the thing being divided by is the divisor. So 325 is the dividend, and 3 is the divisor. Here are the steps. To do long division, you have to divide, multiply, subtract, and bring down. And then repeat those steps as many times as you have to until you're finished with the long division. And we'll tell you what finished looks like at the end. First, we need to divide. So we need to ask, how many times does the divisor go into the first digit of the dividend? In this case, we need to ask, how many times does 3 go into 3? And that's one time. So we put a 1 above the 3 in the dividend, and it looks like this. Next step is to multiply. So we ask, what's the divisor times the thing we just found? In this case, what's 3 times 1? And that's just 3. So we put 3 below the 3 in the dividend, and it looks like this. Next, we subtract the number we just found from the number above it. In this case, we can subtract 3 from 3, which gives us 0, and we write the subtraction vertically, like this. Finally, we bring down, which means we bring down the next digit of the dividend to the bottom. The next digit is 2, so we bring it down next to the 0 at the bottom, which looks like this. And now we just repeat, so we go back to divide. We ask, how many times does the divisor, 3, go into the thing at the bottom, which is 2? Well, it goes in 0 times, because 2 is smaller than 3. So you put a 0 at the top, directly above the 2, and it looks like this. Next is multiply. What is 2 times the number we just found? 0. It's 0, so we put that below the 2 in the dividend. Third, we subtract. We ask, what is 2 minus the number we just found? 0, which is 2. So we put a 2 below the 0 at the bottom, and we write the subtraction vertically again. And then we bring down the next digit, the last digit, down to the bottom, which will be 5, and it'll look like this. Let's go through one more time. This will be the last time. First, we divide. How many times does 3 go into 25, the thing at the bottom? It goes in 8 times, because 3 times 8 is 24, and one more 3 will go over. So we put an 8 at the top directly above the 5, and it looks like this. Second, we multiply. What's 8 times 3? It's 24, so put that below the 25, like this. And then we subtract. What is 25 minus 24? It's 1. So we write that at the bottom, doing our subtraction vertically again. And now we have no digits left to drop down, no more to bring down, so our remainder is 1, and we can write a little square around it. Therefore, 325 divided by 3 is 108, remainder 1. In other words, it's equal to 108 and 1/3. The 1/3 comes from the remainder 1 in divisor 3. And that's regular long division. So what about polynomial long division? It is almost exactly the same as regular long division. We use the same exact steps: divide, multiply, subtract, and bring down. So here's a practice question. Which of the following expressions is equal to x squared minus 3x plus 5 over x plus 1? And then we get a bunch of answers. Well, that fraction is actually just division. In fact, we want to divide x squared minus 3x plus 5 by x plus 1. First, we got to set up the long division. We've got the x squared minus 3x plus 5 on the inside and the x plus 1 on the outside. And our first step is to divide. There's going to be one small difference between this and regular long division. Instead of asking how many times the divisor fits into the digit, we're going to ask a very similar question, which is what times the first term of the divisor is equal to the first term of the dividend. In this case, the divisor is x plus 1, and the dividend is x squared minus 3x plus 5. So we're actually asking what times x is equal to x squared. And that's just x, because x times x equals x squared. So we're going to put an x above the x squared in the divisor, like this. Next step is to multiply. Now we just multiply the entire divisor by the thing we just found. In this case, we multiply x plus 1, the divisor, by x, which gives us x squared plus x. And we can write that at the bottom with the x squared terms lining up and the x terms lining up, like this. Next, we're going to subtract. We're going to subtract the terms we just found from what's above them. In this case, we're going to subtract x squared plus x from x squared minus 3x. The x squared terms are going to cancel, and negative 3x minus x is going to give us negative 4x. So it's going to look like this. Again, we're subtracting vertically. The fourth step is to bring down. We're going to bring down the next available term in the dividend. And if we look at the dividend, the thing underneath the little L, the next available term is 5. So we're going to bring that down, and it's going to look like this. The thing at the bottom is now negative 4x plus 5. And now we repeat. We're going to ask, what times the first term of the divisor, x, is equal to the first term of what's at the bottom, negative 4x? That's going to be negative 4, because x times negative 4 is negative 4x. So we're going to put negative 4 at the top. And now the thing at the top is x minus 4. Second step is multiply. What's the divisor, x plus 1, times the number we just found, negative 4. That's going to be negative 4x minus 4. So we're going to write that at the bottom, like this. Third, we're going to subtract. When we subtract negative 4x minus 4 from negative 4x plus 5, the negative 4x's cancel out, and we have 5 minus negative 4, so that's 5 plus 4, which is equal to 9. So we write 9 at the bottom, lined up with everything, and that's our subtraction. And now there's nothing left to bring down, so 9 is the remainder, and we can draw a little box around that. But what this tells us is that x squared minus 3x plus 5 divided by x plus 1 is equal to x minus 4, remainder 9. It's the thing at the top, remainder, the thing in the box. In other words, x squared minus 3x plus 5 over x plus 1 is equal to x minus 4 plus 9 over x plus 1, plus the remainder over the divisor. And that is answer A. Again, these are the steps. Divide, multiply, subtract, bring down, repeat. Just remember those steps, say them to yourselves over and over and over, and you'll be fine. Now let's take a sharp left turn. We're going to talk about polynomials and their factors. Specifically, we're going to talk about things we can know about a polynomial's factors just by knowing that polynomial's values at certain points when we treat that polynomial as a function. And the things we learn are found using what's called the remainder theorem. Now, there are very rarely questions about the remainder theorem, but there is sometimes one on the test. So if you want that perfect test score, you should pay attention to the next slides. Here's the theorem. Let's say that we have some polynomial function, p of x. Well, if we plug in a and get 0, that is p of a is equal to 0, then x minus a is a factor of p of x. The other direction is also true. If x minus a, where a is some number, is a factor of p of x, then p of a must equal 0. That's pretty abstract and pretty complicated, so let's look at an example. Let me take this random function, f of x is equal to x squared minus 3x minus 4. And this is a polynomial function because x squared minus 3x minus 4 is a polynomial. Now, just from using a calculator, I'm just fiddling around on a calculator, I learned that f of negative 4 is equal to 0, and f of 1 is equal to 0 as well. And if you need to, plug in negative 4 and 1 into the function and prove it to yourself. What the theorem tells us, therefore, is that x minus negative 4, which is actually just x plus 4, and x minus 1 are both factors of x squared minus 3x minus 4. And in fact, if we factor x squared minus 3x minus 4, we get x plus 4 times x minus 1. So the remainder theorem works for this. This theorem works even if we don't know what the polynomial is. Let's say that g of x is some polynomial function that we don't know, but that we do know that g of 7 is equal to 0. Then the remainder theorem tells us that x minus 7 is a factor of g of x. We didn't even have to find the actual polynomial function g of x. We just knew that g of 7 is equal to 0. The remainder theorem is pretty powerful. Now, you may be wondering, what if we plug in a number and we don't get 0? Well, the remainder theorem tells us something about that too. This is the remainder theorem part 2. Let's say we have a polynomial p of x again. Well, if p of a is equal to k, where k is not necessarily 0, it could be anything, then when you divide p of x by x minus a, you get a remainder of k. And the other way is true too. If you divide p of x by x minus a and get a remainder of k, then p of a is equal to k. This is probably more complicated than the first part of the theorem. So again, let's just test the theorem and see if it works. Earlier, when we were doing some long division, we learned that x squared minus 3x plus 5 divided by x plus 1 gave us a remainder of 9. Well, x plus 1 is equal to x minus negative 1. So if we plug in negative 1 into x squared minus 3x plus 5, we should get 9 if the remainder theorem is true. So let's try that. X squared minus 3x plus 5. When we plug in negative 1 into x, we get negative 1 squared minus 3 times negative 1 plus 5, which gives us 1 plus 3 plus 5, which gives us 9. And that's just what the theorem said. And just like the last part of the theorem, we don't even need to know what the polynomial is. Let's say that q of x is something that we don't know, but we do know that q of negative 5 is equal to 4. Therefore, when we divide q of x by x plus 5, x minus negative 5, you'll get remainder 4. Keep in mind, we still don't even know what q of x is, but we do know if we divided it by x plus 5, we would get remainder 4, and that's pretty remarkable. Now a summary. Algebraic fractions. You can simplify, expand, add, and subtract them with the same techniques as regular fractions. Polynomial long division. It uses almost exactly the same steps as regular long division. This lesson is just here to teach you that things are almost exactly the same if you're using algebraic fractions or regular fractions. And then finally, when you plug values into a polynomial, the output tells you something about factors and remainders of the polynomial when you divide by certain things. And that's the end.